So we want to start looking at polar core. Right? I always say this is a very nice example of, you know, mathematicians creating new mathematics, where they found that whatever existed up to their time was either insufficient, or sometimes it's, what would I say, not efficient. Did I use that word? I said insufficient. Yeah, it's inefficient in describing, well, in this case, function, right? So what happened is, I don't know if it was over a long period of time, or whether it was a single person who came up with it. I don't quite know the history, and that's a big gap, when it comes to the research, mathematics history. Um, there's a lot of gaps there as to how these things really happen. Yeah. But mathematicians found a new way of describing, first of all, a point in a plane, and then to describe chords, they found this new way to do it, which we'll refer to as polar. And you'll see we'll talk now about polar coordinates, coordinate, right? Well, we know about Cartesian coordinates, right? And we know about Cartesian functions, or functions expressed using the Cartesian system. That's X and Y, right? So now we're going to look at something called polar coordinates, a new creation, really. And then we will see how we can use this whole idea to now describe a number of curves, right? That well, you would notice that to use the Cartesian system to describe them, they would look rather cumbersome, and you might not be able to easily identify them and so. But using polar coordinates and the polar coordinate system, we can now describe these curves in a very concise way. You even observe patterns, so that we can actually now group the different curves in some categories that make it easy to identify based on their equations, right? You'll see all of that as we go along here. All right, good. Yeah, so we're gonna define polar coordinates. We're gonna plot points using them. We're gonna talk a little about how we can describe the graphs of polar curves, even sketch them. And then, of course, you want to see, well, what we call the Cartesian or the rectangular equivalent to the polar curves, right? We're going to see that as we go along. So let's start with the system. What is the system really, right? And basically what they're telling you now that, well, we used to describe a point in a plane using what we call the X coordinate and the Y coordinate, right? So now we're going to do it a little differently. So if we have a point in a plane, that's P here, right? P there. So you want to describe this point, And I'm going to use X and Y. What we're going to do now, we're going to use R and theta. What is R and theta, right? Well, what we're going to call, before we can do that, we have to set up some references, all right? So OA is what we'll call the polar axis, right? So that's it there, the polar axis. It starts at the origin, and it doesn't have to go in that direction, right? But yeah, we'll use that, right? So from here now, the angle theta is measured going this way, right? You can measure it going this way as well, but leave that for later, right? And the length of this line segment from the origin here, or the pole, to the point is given by r, right? What they call the radius vector, right? Good. And the point now, the point P is going to be described in terms of the length of that line segment, the radius vector they call it, and the angle it makes with the polar axis, right? So that's what we're going to do. We're going to describe, or we're going to define a point in a plane a little differently. We're not going to use X and Y now, right? And keep that in mind, right? That I remember doing a test the other day with some students, and let's say, okay, your graph involves cos theta, and the boy writes cos x, and he's saying, sir, man, I couldn't write theta, so I write x, and so, right? I was telling him x is not equivalent of theta when we're doing polar coordinates, right? So I kind of give him the benefit of the doubt and remark the statement. So I was telling him, when you talk about X and Y here, they mean something totally different, right? So you want to avoid doing that. Good. So let's maybe take some examples and so you're going to be able to see how you describe a point in a plane using this new system, right? And as I said, you should take this as a lesson. You know, anyone can actually create new mathematics, right? You just have to see that need, and there was that need, right? Or even if there isn't a need, but you just want to create something new, nobody can stop you. Nobody owns mathematics or the body of mathematics knowledge and say you can't create something, right? I sent that video, I don't know if anybody watched it, about those two little girls in America, right, who was able to create a new program. High school students doing this thing, right? Just create a new proof for the Pythagoras theorem, and nobody can say, no, you can't do that, right? Nobody has done anything they like in the last 2,000 years. Well, that's what they say. I'm not sure that number was right. I want to feel a lot of the proofs that they have, the 200 odd proofs they say. There were many of them that were created probably a couple hundred years ago. No way. You know, YouTubers got the information from, right? Yeah. So yes, these mathematicians came up with this new system, right? So let's put it to work, right? And these are some conventions, like, and so, you know, what is accepted, what is not. So for the angle, when you measure it counterclockwise, it's positive. Oh, this dash is not negative, right? What's in the bracket? Positive, right? If it is measured counterclockwise, nothing new there. That's how we normally measure angles, right? And it's negative if it is measured clockwise. Nothing new there, right? So they borrowed from earlier trigonometry. Nothing new, right? So it's not hard for people to accept and say, man, you come with a different way to measure this thing, and so to confuse people. No. Right? Then for the radius vector r now, the value of r, right, or the length of the line segment. This one I have to demonstrate with an example, right? Because when I tell you here now, you're not going to quite get it, but you'll see it demonstrated just now. So they're saying that r is going to be positive if you measure from the pole, the origin there, along the terminal side of a vectorial angle. So what they're telling you is, if you have something like this, you're measuring from here straight up, r is positive. But they say r is going to be negative if it is measured along the terminal side, extended through the pole, meaning you're going this way, right? You're going this way, right? You say r is negative. And you see an example just now. And as a consequence, you're going to now see that you can describe a single point, like when you're doing the Cartesian coordinate, a point can only be described one way. With polar coordinates, you're going to see that a point can be described in more than one way, right? So that's something new. So let's take this one. We want to locate the point 345, right? So the line segment is 3 in length. It makes a 45 degree. This isn't hard, right? So this is 45, that's 3. Go ahead. Here it's 3 and negative 60, right? So you measure this way, still 3. Anything difficult there? I don't think so. That's a no-brainer. But let's go to something that will look a little odd to you now. Look here now. You want the point minus 3, 220 degrees, right? So, as we said, minus 3 now, we're measuring, right? So this is 220 degrees. You measure 220 degrees, right? And you measure a line segment that is 3. All right, let me try it. So this is your 220 degrees. Your line segment here is 3. However, they want minus 3. So you're not going to project it in this direction, but in the opposite direction that way. Right? So your radius vector is not going to be from the origin going in the direction of the angle that you measure. No, but the opposite way, that way. Right? That's really odd, right? You following? Anybody following? Does it look rather odd? So here you have a point in the fourth quadrant like, right? But look at it, look at the value of it. It's minus 3, 220 degrees. Right? Look at this one. Minus 3, minus 75. Even more odd. So we go with the minus 75 for. And minus 3 should have been here. But remember, we're not plotting 3, we're plotting minus 3. So minus 3 will be the opposite side of this. Opposite to where the angle is measured. It's this way. So here you have minus 3, minus 75 degrees. Right? Very unusual. Yeah. Take some time and internalize that and see if you can wrap your head around that, right?
Sir, good afternoon. I was about to ask if you can just go it one more time for me, please.
Yeah, these two, right? They're really odd.
They are indeed, sir.
They're really
Thank you.
odd. Right? So, okay. And let me go it a little differently. So I'd probably say, okay, if we had 3 and 220 degrees, we would have measured our 220 degrees. And then measure from here 3 units this way. This point here, let's call it P prime, is going to be 3, 220 degrees. But the point we're dealing with has minus 3 here. So you're not going to measure from the origin here, right? And extend the line, making 220 degrees with your polar axis. No, we're going to go in the opposite direction through the pole here. We're going to go in the opposite direction, right? So maybe if you can't watch this and do it with one go, do when you have positive 3, right? Draw 3, 220, and then say no, because you have minus 3. The radial line, right? Or we call it radial vector, is not really in that same direction, but the opposite direction. Right? So you might have to do it in 2 steps.
So that would be downwards. Continue with the line. Continue in the straight line.
What are you talking about? Here? This one here?
Yeah, the same for us on here. If the minus 3 to 220 degrees, it would just continue the straight line downwards to get a negative.
No, but remember, okay, he's asking a good question. The angle, what? You first have to measure the angle. Oh, and that's funny, yeah? When you are plotting X and Y, you usually say, all right, let me locate where X is and then where Y is, right? So you go here and then you go here and then you pinpoint. Funny thing with polar coordinates is like you're looking at the angles for, right? So first you get the angle for, right? So you get it 220. It's going to start from here. Measure, 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 measure. So 220 is somewhere here, right? Normally you have to draw from the origin here, going in this direction. But because this is negative, you are not going to do that. You're going to draw in the opposite direction. In the opposite direction. You're going to go contrary to where that angle ends. Right? So the angle is measured from here to here. And instead of measuring this way, because there's a negative sign, you're not going in this direction. You're going in the very opposite direction. Right? So that's another tweak or a little peculiarity of polar coordinates. You don't look for the force, okay, you're trying to plot -3 force. No. Do the angle force. Right? That answers what you were saying, sir?
Yes, that's it. That answers it.
Yeah. And it's good when you see, you're wired a certain way and then something new is presented to you that's different, that is, kind of wrestling with your mind and there. And that's a good thing. That is when brain development is taking place, right? And that's why sometimes we fail our better students in school. We be teaching them what they already know and what they just easily grasp. You're not helping them, right? You're not helping them. That's why sometimes the brighter students, they come to UG, and sometimes the poorer students who, they may come with a grade 2 and 3 and pass the grade 1 student. I don't know, well, you wouldn't know that, but I can tell you that a lot, just to deviate for a second. I have experienced that a whole lot, where these brighter students will come with something 10, 15 grade 1s, and so they do well at CXA when they come to UG. This is what happens sometimes. Burnout and so, right? They come, they're tired of 10, 12 lessons and, this big studying at CXC. They only needed 5 subjects to get into UG. Right? And they were bright students, and you weren't challenging them really. You weren't challenging them. They would get the 15 grade 1s whether you teach or not. Right? Most of them are like that. Those students who get a 15 grade 1, you don't even have to teach one day in class. They're going to do the 15 grade 1 anyway. But guess what? Because they were never challenged, when they come to UG and they're challenged, what happens? Very well, because the other students were used to being challenged, right? And they're used to their brain being, people taking what they had in mind, throw it out, teach them new things, develop their brain.
This thing is right. It also tying with the rule that a positive rotation is anti-clockwise, right? The tying with that rule. When you go the other way.
Yes. Well, okay. No, there is nothing new there. Like the negative 75 here is a positive rotation, if you want to say, right? You're going this way, clockwise. However, after you have done the angle, you get negative 75 going this way. So the -3 now, you should have, well, okay, if this was 3, the length would have been here, right? Or the point would have been somewhere here. But because the value of R is -3, you have to go contrary to where this angle is, right? You go the opposite direction through the origin and go in this direction, right? 3 units. And that's how you get the -3, -75. Right? Take some time. It will take some time for you to fully accept and grasp this thing. That's the only little difference there, right? As a matter of fact, though, you recognize now that you can actually describe the same, what did I do with my pen? Oh, yeah. You can actually describe this point now, and can somebody tell me? How can I describe this point differently now? P is also what? 3, and what angle can I put here? Just take away 180 from 220, right? And you get what? 40 degrees?
Yes, sir. Negative 40.
Yes, sir.
No, positive 40, what? Like it, what? Going this way, 40 degrees, right? And 3 units this way. Oh, I think I did say 180 minus 220. Okay, the other way around. 220 minus 180. So this here is 40 degrees, and the length here is 3 units. So 3, 40 degrees is the same point as minus 3, 220 degrees. Right? Keep that in mind. And of course, you can keep rotating wrong and wrong and have an infinite number of angles, right? And so let's stick with, these two alternatives here. Yeah. Similarly here, this one here, what will this be? Take away 75 from 180. What's that? You'll get 3, 105 maybe. I hope my arithmetic is right. Right?
105, sir.
105 or
Yes, sir. 105
Yes,
is
sir.
correct.
yeah. So you see, so this point can be described as 3 and 3, 105 degrees. Right? So yeah, you can describe it in more than one way. And again, that's another little strangeness of polar coordinates, right? In the Cartesian coordinate system, you can only describe it one way, right? X must be this and Y must be that, and that's it, right? For some, with simple minds, they'll say, we should have stick to that, right? But there are others who say, well, you stick to simplicity, you're going to get more complicated and bend the human mind, Good. So let's see the connection between the two. So we have here, all right, you have a point, and the point is r theta, and the equivalent is xy, right? So we're going to do a little bit of trigonometry. You can see it here already. R is there, theta is there, that's y, that's x. The trigonometry is very basic. So cos theta is x over y, sin theta is y over r. What did I say? Cos theta is x over y. I meant x over r, right? And from that, you rearrange, you get x equal r cos theta, y equal r sin theta. You use the Pythagorean identity, you square both sides, and so, right? You end up with this formula. R squared equal to x squared plus y squared, right? You want to make r the subject, not r squared, it's up to you, right? And then the angle is going to be tan inverse of y over x, right? You see any relationship there, how to convert one to the other. Nothing hard here. So we're going to apply it to some examples in just a moment. How will we convert maybe a point, in Cartesian coordinates to polar coordinates and vice versa, right? So we need to remember all of it. Right? So look at this one. You have the point 6, 150 degrees, and you want to write that in terms of x and y, right? So simple. X is equal to r cos theta, which is 6 cos of 150. That's some number. And y equal r sin theta, which is 6 sin 150. Again, that's some number, and they did it here, right? X is minus 3 root 3. Y is 3, right? So that's our simple conversion here. I want to write it as minus 3 root 3, right? Simple as that. Conversion shouldn't be hard. You just gotta remember, x is equal to r cos theta, y is equal to r sin theta. Once you remember that, and then remember, you're doing a test, you have your formula sheet right near you, right? You can go right ahead and consult it. Let's go the other way. So you have a Cartesian coordinate, pair of coordinates, -4, 3, and you want to change it to polar coordinate, right? So you got to get r, you got to get theta, right? So we earlier said that you use Pythagoras theorem, get r. So -4 squared plus 3 squared, root of it, you get 5, right? And the angle is tan inverse of what's y 3 over 4, 2 over -4. Notice they have a negative angle, but instead of using the negative, right? And you have to use a little bit of common sense here, right? Even though they give you a negative here, you could have written it with this, right? You could have written it with this, right? Anybody can think of how we could have written it? Just a moment. So knowing that the thing is in the second quadrant, and they want to use this 5 unit, they want to use a negative, right? So the point is really 5, positive 5, 143.1 degrees. Now you see how they get that, right? Instead of using the negative 43, negative 36, negative 36.9, instead of using this, right? And then in that case, you would have to use -5. And it will look ugly now, right? You get -5 minus 36.9. That would look ugly. So this writer is saying, no, let's not go that way. Use the positive value, right? The 180 minus the 36.9, right? Get the 143.1 and use the positive 5 instead. That's what it is. Positive 5 and this obtuse angle, right? Nothing is wrong with you saying -5 minus 36.9. Don't rely on just the mathematics, right? Be sober and think that, you know what? Where is point really there? Right? This point is in the second quadrant, right? We tell students sometimes when we're doing some mathematics, like when we were doing the when we were doing algebra, I was doing some algebra with some students in Warby. And like in the multiple choice questions and so, I might put something like this, you know. All right, the modulus of x plus 1 equal -1, right? And the students are going to show you a whole set of steps and you see them. And I said, hold it. Why are you doing all of this? You know, just because you know some mathematics, they're doing mathematics. I said, no. Look at the thing. You know, look at the thing and be sober. Can you have the modulus of a number being -1? You can't, and therefore, there's no need for all the steps. Because mind you, when you do the steps, you do have answers. The mathematics is going to churn out answers, right? But you just have to know that, okay, that answer is a nonsense answer, right? However, when you're using your AI to fool me, like you're doing, you know that the AI gave you nonsense. You tend to know, right? With some kind of, and I always tell people that I may not know something, right? And I have students research it. But when they present something to me, I know they're talking nonsense. I have a gut instinct because of my exposure to mathematics over the years. You know, tell me, you in real life, you know when somebody's talking stupid. You know, something they say is not adding up. And you say, you know what, hold it. Don't bring that crap to me. You know, and you start to question it. I remember, let me give you this quick story. I was in a master's, one of these presentations, right? A set of students were presenting to a group of us. And they were talking about their idea for, I think it was a proposal, you know, for their master's thesis, right? So there's this girl started to present something. I can't remember what the topic was. When I watched this girl presentation, I thought to myself, like, I don't know nothing, right? I felt so, foolish. I said, what? Where is this fancy thing coming from? So there was a guy, I don't know if you all know him from Eugene Town, Dr. Hine. He supervised me for my master thesis as well. And when the whole presentation is finishing, the others were talking and they were praising her and so on and so on. He said, could you go back to, and she had an idea for, we call it, a conceptual framework, right? She had a diagram. And he said, can you explain this diagram to me? And guess what? The girl couldn't explain that. So the man said, it's a conceptual framework. It's the idea there of the entire thesis. And if you do not understand and cannot explain your conceptual framework, you don't have a study. The whole thing was thrown out because it's not he doesn't know what the thing is talking about. He's just asking her, tell me what this thing is saying. Right? And she bluffed her way out in front. She had a fancy diagram and she said she's going to relate this to that. Right? I remember doing something very similar when I did mine. Because what I was doing, just to give you an idea, next year you're going to do some research yourself. And I was looking at students' beliefs, right? Students' beliefs. And how it matches up with their performance, right? And I also had in there, I wanted to look at the teacher's beliefs, right? And he asked me that question, how am I going to match up the teacher's beliefs with what you going to match it up with? What you going to correlate it with? And I was like, I couldn't answer that. And he said, once you can't answer that, you got to take out this whole teacher thing because the students, you will ask the student a question and he will obtain a score for some test or whatever, and you will match it. Each student has a match. But how do you match what the teacher believes? What do you match it with? And then I realized, the stupidity of my framework at the time. And I had to get rid of things, right? Because sometimes in research you want to explain everything. He says, look, there might be a way to match teachers' beliefs with something, but it's not in this research. It's something else. Okay, so look, we're converting now equations now, not just a point, but an equation, right? So we're going to first convert an equation that we're familiar with. We're familiar with X and Y business, right? And now we're going to convert this to a polar, a polar coordinate form, right? So we got x squared plus 2y squared equals 6, right? X squared plus 2y squared equals 6. How do we do that? Well, we knew earlier, and I think we got this from remember that the conversion equation? X is this, y is that. All you got to do now is take this, put it in the place of x, put it in the place of y, and do some simplification, right? So, you do a little thing there, you do a little thing there, factorize out that, and well, that's what there's a 2 there. I wonder what we'll do with that. Okay, we can't do nothing more about that. If this 2 wasn't here, it would have been nice. But the 2 is there to disturb things. All right, we have to leave it at that. All right. I was going to say we're going to simplify the cos squared theta plus sin squared theta equal 1, but there's a ugly 2 in the middle here, right? So in this case, it doesn't look any simpler. It looks horrible, right? I wonder what this is. Wonder what that is. Type it in Desmos and see while I'm talking. All right, let's do the opposite. We're transforming a polar equation now to a Cartesian equation, right? So we have R equals 8 cos theta, right? Good. So we're going to take that now. We're going to put R is, what is it? Root of x squared plus y squared. And we know that cos theta is x over r, right? So, all right. We put all of that in the equation, right? And we're going to get this horrible looking thing. But when we finish doing all of that, we can do some arithmetic, you know, square up all two sides and whatever else. And um, okay, this is equal to this. I wonder how they got it. You square both sides of this goal. And no, you didn't square both sides. No, they simply carried this over times that. Look here. All those little thing they were cross multiplying. You take this and you multiply that. So this by itself, the square root sign is going to go, and this 8 left with the 8, right? Yeah. And it looks like that, right? X squared plus y squared equal to 8x. I also do not know what that graph will look like. You can always type it in though. Type it into Desmos. Type in this into Desmos, see what it looks like. Type in this into Desmos, see what it looks like, you know? Yeah. With all the technology we have, while I'm talking, somebody could very well do that and come back and tell us the answer. Right, okay, so look at this one. This is the last one here. We want to transform R equal 5 over 2 sine theta minus cos theta, right? So this thing here. Good. So we know cos theta is that, sine theta is that, so we just put them there, right? Let's see what they did. No, well, they didn't do that first. They cross multiply. You have R times this equal 5. And then you put in the values of cos theta and sine theta. And then it simplifies nicely because the R is going to cancel those, right? And you end up with a nice, oh, that's a straight line basically. Well, look how complicated it is here. But it turns out to be a simple straight line for it. Right? And these are, I guess these are well, these are exercises like, you know, you can do them in your own sweet time. Good. What about some graphs now? What about some graphs of polar equation, right? And there's some categories because of there's some similarities with these graphs. They were able to kind of categorize them, right? Just like how in Cartesian coordinates, you have conic sections. We're gonna touch on that a little, maybe Friday or when. You know, you had the circle, the parabola, and ellipse, and I think what is next? So hyperbola. I think I took out a mark from somebody. This spell the word ellipse as eclipse, right? You lose a mark for not knowing to spell something like that, right? Yeah, sure. So first we talk about the Rose curve, right? Something called the Rose curve. And Rose curves, they take the form of R equal A sine n theta, or R equal A cos n theta, right? Either of the two. They tell you if n is an odd number, there are n leaves. If n is even, there are 2 n leaves. Now, what I want you to do in your own time, right? And sometimes, you know, you have to do some of these investigations to develop your own self, right? Try some values here for A and N. Try some values in Desmos, right? You are familiar with Desmos. And you will see, I'll dazzle your eye a little because I want to skip down to the graph of what it looks like, right? So the Rose curve will look like this. So look, right? So you have what here? 1, 2, 3, 4. 1, 2, 3, 4, right? And this one, that's an even number. And then this one is an odd number, right? 3, right? So that's what the roses will look like, right? That's what, and that will be determined by either the n, right? N. Remember, there's an N in the formula. The N, you say if N is odd, you get NA. And if N is even, you have 2NA, right? I want you to check out on your own in using Desmos. Figure out when you have sine here and you have cosine. How is the graph different? I don't want to tell you everything. I'm a big people, right? When you have sine and you have cosine, what's the difference with the graph? Right? What's the difference? And when you change N from odd to even, what's the difference in the graph? Right? So go into Desmos and do some graphing, right? Do some graphing. Oh, I just want to share this little bit. I think I need to go into Desmos. Give me 1 second. I just want to go into Desmos and just show you something that you might need to change. R equals A sine N theta. All right. I'm just writing A cos N theta, right? So I'm going to stop sharing for a moment, right? And I want to go over to Desmos just to show you something. I'm going over to Desmos. So I'm in Desmos. Share, right? So you are used to this kind of thing, right? You're used to the Cartesian coordinate system. So what you might want to do when you're dealing with polar coordinates, you might want to do this. Go to grid, right? Let it look like this, right? You might want to do that. And you will go with, okay, R equal, what is it the idea? Let's say 2 sine 3, okay, let me go 3 theta. 3 theta, right? See what it looks like? You can change the number. Look at what happens when I put maybe 5 here. What changes on the graph? You need to do that investigation, right? So I change the A, then maybe I change this to 4. What happens, you know? Then you might want to try changing this to, let's say, cos. What's the difference? I wouldn't tell you, right? I want you to investigate it for yourself and figure it out, right? And that's for all the categories of polar form. Come to Desmos and fool around here, right? I don't mean fool around, I mean investigate, right? And see what happens when you change like the 5, the 4, the cos to sine. See what's happening to the graph, right? And that will help you to understand the various variations in the equation, right? And relate it to the graph, right? So let's go back. I notice mosquitoes are coming down already now. I don't want to have a 6 o'clock class in here. So I don't know. Yes. So here it is, right? So we got a rows there. That's the general formula, like of the whole family of chords, right? And then you have what you call the limison, right? The limison has this form now, right? R equals B plus A sine theta, or R equals B plus A cos theta, right? And then they're telling you some conditions now that the limison is going to be a cardioid if A equals B, right? And again, I want you to do this investigation, right? And that's small children here. And then what happens when B is greater than A? What happens when B is less than A? What happens to it, right? So some of the information is here, yes, but I want you to go to Desmos, put in some numbers for A and B, put in a negative here, put in a positive here, put a lower one, put a higher one, you know, change from sine, change to cos, do all of that and see what happens. How do you get this cardioid, right? And again, if I were to just that's the eyes a little, and I'll just dazzle your eyes a little, just to show you the graph, the limison and the cardioid, right? So this is the limison generally, and the cardioid, when you take out this loop from in here, right? Take out the loop from in here, you get a cardioid, right? See it there? Good. And then you have the others, right? You have what you call the lemniscate, right? I hope I pronounced that. Lemniscate. Yeah, it's of the form r square, notice now, equal to a square cos 2 theta, or r square equal a square sine 2 theta, right? And what you'll figure out this, I think, these are what we call it bow shape, that bow shape. You always hear bow tie. You make a bow tie, or you girls would knock your rib. Oh, your shoelace too. You have that little two petal thing, like, well, that's what it is. Let me just show you what it looks like. Where is it? Oh, look at it. The lemniscate, right? That's what it looks like. So you would try cos and sine, change it and see what happens to this core, right? Change the numbers a, and so change the value of it and see what happens, right? So that's what your lemniscate would look like. And then lastly, you have, coming back to this here, you have what you call it, the spirals, right? The spiral of Archimedes, the reciprocal or hyperbolic spiral, the logarithmic spiral. You know, I don't want to get into too much detail, right? But the spirals will look like, scroll up again, right? This is what they will look like, right? So those are basically the broad categories of polar cores we'll deal with, right? We'll have the roll, the limison, and the cardioid. They're kind of related. The lemniscate and the spiral, right? Those are like, we'll put it as four categories, like. Good. And well, you see their graphs, what they will look like. But I'm tasking you with, investigating these equations and their corresponding graph. Play around with the A's and the cos and the other values in the equation, and see what happens to the graphs and so on, right? They're rather fascinating. You have the tools long ago when we had to do this. We had to do this with hand body, right? You had to take graph paper and draw the thing. Then have the radial graph paper that we had, that grid where, right? I remember one time I visited Ensor, and they had it there, and I was so fascinated when they gave me the thing to do a little exercise. What do you think I do? I stash off two for bring home because I want to impress my students. So bring it and show them, and so on. My students were so elated. Today, the thing is at the tip of your finger. Well, how am I saying that? It's at your fingertip, right? You just have to click a mouse, go on to Desmos, and you have the thing all visualized there for you, right? What I didn't talk about here is a little bit on area. Like, you want to know, what's the area in this little loop here, or in this part here of the core, or maybe one of these loops here, what's the area in there? Now the videos I'm going to send you, they're student presentations. I'll edit them because I made some comments at the end. I'm going to edit them and so a little tomorrow, maybe tomorrow, Wednesday the latest. And I'm going to send it to you, right? And you're going to see a lot of, they aren't the best of presentations, but they're your peers, huh? And you will see some presentations here in Bobby. They're not bad, but you can learn something from them. Lots of examples, and they did touch an area. So you are going to get some exposure there to calculating area. And fortunately, you have done calculus. So the integration that is going to be involved is not going to be so difficult, for you. So that's a plus, that you are doing this course after you have done calculus, right? But there's a little bit of integration inside, right? And you're supposed to do some area under a curve using calculus. Good. So what will happen tomorrow? As I said, I'm going to send you some notes. It's late now. I'm going to send you some notes on polar coordinate, polar curves, as well as I think chapter that I'm from the book I'm extracting it from. The chapter has inside conic sections as well, right? So it's a good review. I think you have done quite a bit. When you were doing conic sections with your other course, the course before this, did you go as far as translated axes? Did you go as when you translate it? Okay, the conic sections are not all centered at the origin. Did you do when it was like maybe a 2, 3 or -1, 4? The center is no longer at the origin. Did you do that? Nobody's answering. Y'all are hearing me when I ask that question? Or you can't remember?
No, sir.
Oh, you didn't do that? Okay, you just did the conic section centered at the origin. All right, that'll make this
Yes,
course a
sir.
little longer. My students here, I tried to push that in the previous course. It helped with this course, you know, that it will take us a little while to do that. Good. So I'm going to stop here, right? Stop here. Let me stop the recording as well.